Hi guys. So 3.5 is called related rates. Okay, so these are going to be related rates with story problems. So the idea is that you're going to be finding the rate of change with respect to time. Okay, so that's a big point right here is every time you derive anything, you're going to be deriving it with respect to time. So instead of respect to x, it's being derived in respect to time. Okay, so quick procedures here for what you're going to do is you're going to start by drawing a figure if you need to and define all your variables, and then you're going to come up with some kind of equation, and you're basically going to end up deriving it in terms of your time, and then you will derive everything implicitly. Okay, so what we learned in the last section, and then you'll end up plugging in any numbers that were given to you in order to solve for whatever question it is they're asking you. Okay, so right here is a bunch of formulas. Notice that everything is geometry. So basically it's going to be the idea of, some kind of shape. Let's just say, for example, a triangle, right triangle. Um, if it's going to be getting bigger at some specific rate or smaller, okay, or, area or volume of these things. Okay. So first thing, question number 1. This is basically given to us as the area of, let's see, s squared. That's the formula for the area of a square. Okay. So they're giving us this initial information and they want us to find the dA dt. Okay. So we're going to start this off, and we're looking at this formula right here. Okay, so that is the equation we're going to use. This information is stuff that we're going to plug in after we do our derivative. Okay, so if I derive a in terms of t, it's going to be dA dt, because the derivative of just simply a would be 1. Okay, then on the other side I have the derivative of s squared, which is going to be 2s, and since I derived the s, I have to write it as ds dt, since I am now working in terms of time. Okay, so that is the derivative. So now all I have to do is plug in these two pieces of information that is given to me. Okay, the s value is 4, the ds dt value is 3. So then I just multiply that together, so I have 8 times 3, and that would give me 24. Okay, so you'd normally label this, but since we don't know the increments, we'll leave it as 24 for now. Okay. Okay, so B is really similar as far as information that is given. These are variables that we're going to plug in after we take the derivative of our equation. Okay, so they ask us for dy dt. Okay, so if we take our equation and derive, we have a product rule right away. So I have an x times a y, so it's a first d second plus second d first. Okay, so remember I'm deriving things in terms of t. So every time I derive any variable, I'm going to say dx dt or whatever variable. Okay, so the first is x times the derivative of the y. So derivative of y is 1, but I'm going to multiply by dy dt. So plus the second times the derivative of the first. So again, derivative of x is 1, which I'm not going to write, but then since I'm taking the derivative of x in terms of t, I'm going to do dx dt. Okay, so I'm going to set that equal to the derivative of 12, which is 0. Okay, so step 2 now is going to be plug in any information that is given to me. Dx dt is -6, and the value of 4, or y is 4. Also from this equation, if I have x times y is equal to 12, and the y variable is equal to 4, that can tell me what my x variable is. Okay, that tells me that my x variable is 3. Okay, so it's giving me more information than really initially shows. So I'm going to plug in all 3 pieces, my dx dt, my y, and my x, into this equation here. Okay, so the x value is 3. dy dt is what we're going to end up solving for. The y is 4, and dx dt is -6. Okay, so now I can solve this. So I have 3 dt, oops, I said that wrong, excuse me, y dt. That just fell down. Okay, and then this is plus negative 24. I'm going to subtract that to the other side or add that to the other side. So since it was a negative 24, I'm going to add it to positive 24. And then I would just divide by 3. So that tells me that dy dt is equal to 8. Okay, and again, remember that you're finding a rate. Okay, so if it was like feet in seconds or whatever, it would be feet per second. All right, so now they actually get in and give us an actual story problem, which involves a boat. Okay, so it's got a windlass that is used to tow a boat to the dock. So this diagonal piece is the rope. The rope is attached to a boat at a point that is 15 feet below the level of the windlass. If the windlass pulls the rope at a rate of 30 feet per second, okay, so right away I see this 30 feet per minute piece. Okay, so that's a rate, and it's specifically telling about the windlass, which is the rope. Okay, so I can say immediately that the variable representing the rope is z. So I can say that dz dt is equal to 30 feet per minute. So at what rate is the boat approaching the dock when there is 25 feet of rope out? Okay, write a sentence to explain the meaning of your answer. All right, so hopefully at this point you've kind of come across the fact that we're dealing with a right triangle. So the formula for a right triangle that we're going to use is going to be Pythagorean's theorem. Okay, so specifically using the variables that they've labeled here, the x is going to be the distance from the dock to the boat, so x squared plus 15 squared. Now that distance does not ever change, so it's a constant value, and that's going to equal the z squared. Okay, they also gave us the fact right here that at some point in time we've got a z that is equal to 25. Okay, so that's going to be information that, like in those previous examples, we'll plug in after we take our derivative of our function. Okay, we can also use this information and solve for the x value. So since I have x squared plus 15 squared is equal to 25 squared, we can solve that. 15 squared, hold on, I'm going to screw that up. 15 squared is 225, and 25 squared is 625. So then if you subtract those, you get 400. Ooh, and I can do that. So the x value would be 20, and we would only use the positive value because we're talking about a distance. We wouldn't use negative. Okay, so those are pieces of information that we're going to eventually plug in after we derive the equation. Okay, so if I derive this, I have the 2x, or x squared, so the derivative of that would be 2x dx dt. The derivative of our constant piece is 0. The derivative of z squared would be 2z dz dt. Okay, so there is my derivative. So at this point, I'm going to plug in the information that is given to me. I've got x, z, and dz dt. So what am I going to be solving for, which, by the way, was the rate at which the boat is approaching the dock, which is this rate of change, which is the dx dt. Okay, so if I plug in my x value of 20, dx dt, I'm going to say is equal to, since we got 0 there, 25 and 30 for my rate of change. So we multiply that out, and that gives me 40 dx dt is equal to, let's see, that would be 50 times 30. Oh, here's a piece, and I totally almost forgot about this. If we talk about this change, okay, the change is going in at a rate of 30. So what's happening to this length? Is it getting bigger or is it getting smaller? Okay, it's getting smaller. So this rate has to be a negative value. So I need to put that in as a negative. Okay, so that makes this negative 1500. That's a big piece of information. So if I do negative 1500 divided by 40, that gives me negative 37.5. Excuse me. So then I got to label this in terms of my story problem, so I have feet per minute as my rate. Okay, so negative is implying that it's going to the left, it's getting smaller. All right, the last question here. Okay, so this is gravel, and this machine is pouring this gravel onto this conical pile. Okay, so conical pile is giving us information about what the shape here is. Okay, so it's saying it's a cone. Okay, and we're talking about the volume of a cone. So if you look back above, you might remember that the volume is equal to 1/3 times pi times r squared times height. Okay, so it says the gravel is falling at a conical pile of, or excuse me, on the conical pile at a rate of 10 feet cubed per minute. Okay, so that's going to be my dv dt. Okay, and I should think about its positive or negativity-ness right here. It's adding to the pile, so it's going to be a positive rate. Okay. At all times, the radius of the cone is twice the length of the cone. So that's an interesting piece of information. We can say the radius is equal to twice the height. Okay, so the cool thing about that is that really allows us to put some more information into this. Okay, so I can solve for one of these two variables. So it's asking us to find the rate of change of the height. Okay, so what I'm going to do here is I'm going to replace my h, or excuse me, my r. I'm going to do substitution into this and replace that, so that's my equation is in terms of h rather than in terms of r. And then I'll talk about what it says right after that. So if I plug that in, I have 2h squared times h. So if I simplify this, on the inside I have the 2 squared, which is 4. I'm going to pull the 4 out and put it with the 1/3, so that would be 4/3 pi. And then I have h squared times another h. So it makes a total of h cubed. Okay, so now this is my new formula in terms of h. Okay, so continuing through this sentence, it says when the radius of the pile is 6. Okay, so if the radius of the pile is 6, what would the height be? Okay, the height would be 3. Okay, so that's going to be information that we can plug in later, those two things. Okay, so I'm going to go ahead and derive this. So the derivative of v is 1, so I have dv dt. Okay, so this is going to be a basic rule. I have one constant. Okay, so this is kind of like one little piece here. When I derive this, I'm going to do the 3 times this piece that's in the front. So if I have 3 times 4/3, the 3's cancel, and I'm left with 4 pi. Okay, remember pi is a constant number. And then I have times h, and I'm going to lose one of the exponent. So squared, so that's the derivative, and then don't forget dh dt. Okay, so there's my derivative. So now I'm going to plug in the given information that we found. So my h value we said was 3, so I have 3 squared. dh dt is what we're looking for. dv dt over here is 10, so we're going to set that equal to 10. Okay, so if I solve that, I'm going to just type this into my calculator. Just divide by this whole 4 pi times 9, I guess you could say, or 36 pi. So 10 divided by 36 pi is going to be my dh dt. So if I plug that in to the calculator, I end up getting 0.088 feet per minute. So remember, I always want to round to 3 decimal places. And there is my change in height in terms of time. Awesome. All right, so for your homework, what I would like for you to do, okay, is I would like you to do the first 3 questions. So 1, 2, 3.